Guys, I got a quick question for you. I want you guys to know what happens when you have one mole going in and two moles coming out. So what I mean is, if you started with pure A and you have a reaction like a decomposition reaction or anything that differs in the number of moles between the reactants and the products, what's going to happen to the volumetric flow rate as that material is flowing through? So that's what this video is all about. It's going to teach you how to account for this in your calculations. I know it confused me when I first saw it, but hopefully this can clear it up for you guys. So here we go. So right here I've written down the ideal gas equation, the famous, plentifully used equation for thermo. It's back. Okay, but here's the dealio. When you're dealing with flows, it's okay to do this. Now Q here means volumetric flow rate. I hate writing little v because it looks like volume. And especially when you're sizing reactors, it's not a good idea to have a little v next to a big V. It can be very confusing. Now F has been our molar flow rate, RT. There we go. So that's the equation we're going to be using to reveal the truth, per se. Okay. So on the beginning of the analysis, what you want to do is you want to write CT over CT sub naught. And we're going to take an analysis and equate things together. Over here, what we're really trying to do is say CA over FA over Q, right? This is just a general equation. And for Q, we're going to come up with a big equation for that. That's going to have conversion in it. It's going to have parameters that will be responsible for the speeding up of the flow rate. And again, the flow rate is changing throughout the reactor, so we need flow rate as a function of conversion, as a function of other things. Okay, and you'll see what those are. So, and that's going to happen from over here. So CT, right? Just like over here. I'm not going to leave that circled. Okay. You can write it like this: FT over Q for the total molar flow rate of total moles over the volumetric flow rate. Now over here, the total moles initial, which is usually just pure A, but it can be different, over Q naught. And one more thing we got to do now. Now looking at this equation, we can rearrange some terms, right? So we got FT over Q, and as you see in generality, F over Q is going to equal to be P over RT. So in the case of FT, you're going to have P over RT, and in the case of FT sub naught, you're going to have P sub naught RT sub naught, like this. So this is the little bit we're going to take and we're going to solve for Q. Okay? So then what you do is you go, okay, FT over FT sub naught, just rearranging the left-hand side. And this would be Q sub naught over Q. Remember, we're solving for Q. P over P sub naught, like this. R's are going to cancel. This will cancel with this. And then you got T sub naught over T, right? So now it becomes solving for Q, so we can plug it into that CA equation that I'm highlighting right now in green. We got to plug that in for Q, right? So let's solve this equation for Q. Well, if you solve it for Q, you realize it's going to be like this: Q sub naught. Let me make sure I'm doing it right. FT sub naught. This will be P sub naught over P, T over T sub naught. This is your equation as it is. But here's the thing. Let's come up with a different term for this guy, or a different way to express that. Now, I could say that the FT is going to be equal to the FT sub naught, and this is going to be, let me think about this for a second. Okay, so it's going to be plus FA sub naught, this new parameter gamma, and then times X. Now I'm going to go into what gamma is, and hopefully this little bit will make sense. Okay, here we go. So gamma is the moles total changed, right, to moles of A reacted. Basically, it means the change in your moles in the reaction to the moles of A that reacts, right? So let's put it this way. If I had A goes to form B plus C, what's going to end up happening is that you have 1 mole being fed and 2 moles appearing, which means that you have 1 mole total changed to yeah, one mole is total changed. Okay, so then this would be equal to 1. Now, if this was like this, it'd be -1. Because then you'd be saying, okay, 2 went in, 1 comes out, and the change was -1. Okay, here we go. Now, as you can see from up here, let me highlight it. We're solving for Q. We need an expression for Ft over Ft sub naught. We only have an expression for Ft. So then what you want to do is divide both left and right by Ft sub naught. So then you get Fa sub naught over Ft sub naught, the little gamma, times x. So Fa sub naught over Ft sub naught is actually equal to your molar fraction, Ya sub naught, the molar fraction of A going in. Okay, so we can rewrite this. I'm having trouble with my marker. Like this, right? There we go. So now we got an expression for Ft over Ft sub naught. So I'm going to bring down the equation from the top. Hopefully this works. I'm praying on it. Let's see. Yay. Cool. I'll bring that down over here. There we go. Okay, so let's plug in Ft sub naught into this equation. But there's one thing. We can also group these terms and call that epsilon. So epsilon is equal to Y gamma. Okay, now you got this equal to Q sub naught. And this would be 1 plus e to the x, where epsilon is equal to the delta times the molar fraction, Ya sub naught. Like this. So over here it's going to be P sub naught over P, T over T sub naught. Now this is where you can deal with isobaric and isothermal. You can make the assumptions by crossing out the temperature terms and pressure terms, but we're going to leave it in as a whole. Okay, so the rest of it's easy. Ca is equal to Fa over Q, our general expression, and now we're going to plug in Fa, so in for Q. We're going to plug in for Q. 1 plus e to the x, and now I can write it like this, where I flip those fractions, because if they're in a denominator and the numerator, they're just a mirror of each other. There we go. So Ca is going to be equal to, now for Fa, I can write FaO 1 minus x, like usual, like we did for a liquid. But as you can see, that volumetric flow rate term is now compensating for the speeding up of the gas. And there you go, there's your equation. Now we can simplify it a little further by taking the molar flow rate Fa naught and making it the Ca naught. And that's probably for the best. In other words, Ca naught times your volumetric flow rate, initial, 1 minus x over Q sub naught, 1 plus epsilon x, P over P sub naught, T naught over T. Now what we can do is we can cross out these guys. Okay? And now our final form of the equation is complete. So given a conversion, an initial concentration, a reaction equation where you can get epsilon, and then your pressure conditions, which will come in later chapters when we use the Ergun equation, and for isothermal reactors, or for isobaric reactors and thermal changes, you can count for in these terms. It's very important that we do that. So yes, so let me circle it for you guys. This equation right here is the concentration, the new concentration term for when you're dealing with gas phase reactions. And on a quick note, as you can see for liquid phase, it was simply just this. And it did not have this, it did not have this, it did not have this, didn't have that, and it didn't have this. So these are all new added terms when you're dealing with gases. And that's kind of the way to understand that. If you're dealing with gas, you want to account for the change in pressure, change in temperature, and the change in the number of moles. And you have three terms, check mark, and check mark, that deal with these when you're dealing with gases. So I hope this is helpful. And remember, this is your equation for gas phase when you're dealing with concentration. And in ideally all cases, with plug flow reactors, you're going to be plugging that term in for concentration, not simply just what is written here underneath.